All right, so something that you will have to have here, don't write this down. Something you will have to have in this class now is some calculator, okay? I would suggest if you're a handheld person, get a TI 384. Don't go buy one right now. Borrow one from somebody if that's your option. If you have one of these, like if I was going to buy something, this is like the cheapest, like $10, $12, okay? I would urge you not to buy something because we can do the same thing with Desmos, okay? But you just have to get your computers out and use your computers, all right? But these calculators, I'll show you how, I'll demonstrate how to use these and these if that's what you have. There will be times where we have to rely on the calculator because the values that we need to get back aren't things that we're going to have committed to memory. Okay. All right, so if you have the notes printed off, I'm going to do a little bit of skipping around. So if you can find that slide there, that's where I want to start. Basically what we're going to do when we talk about the trigonometry, we're going to be referring to sine, cosine, and tangent on our calculators. Okay, but I think it's important because I can show you all the steps. I can teach you guys to be robotic. I can teach you to be. I can go through the monkey see, monkey do type thing where I do it, you do it, I do it, you do it, and then you'll learn how to do something. Okay, but you won't learn the why, or you won't learn where these values are coming from. Okay, because it might seem somewhat kind of maybe magical that when I type in sine of 30 on my calculator, it spits back 0.5. Or when I type in sine of 60 on my calculator, it spits back 0.8666. Okay? Or I think I said 126 is there. But if I type in sine of 45, it spits back 0.707. Where are those numbers coming from? And why can I use them in any problem that I come across, regardless of how big the right triangle is? So that's what I want to investigate today. Maybe we get into some calculations, maybe we don't, but I want to make sure that we understand where these values come from and why we can use them the way that we do. Okay? I think if you understand that part, that's the mathematics. Okay? The other stuff is computing or arithmetic, right? I think understanding the mathematics part of things, the reasons of why and how make the calculation stuff a little bit easier for us, okay? So these, when I say the sine of an angle, so the first thing we're always going to do is they're going to give us an angle to view, okay, to look at. So right now, they're saying angle A. So I'm going to view angle A. Okay, so you see I've highlighted it. I just want to draw my attention to that. You then start labeling sides in reference to angle A. So what you're going to do is you're going to identify three sides. You're going to find the hypotenuse. That's the easiest one to find, right? Hypotenuse is always the across from the right angle. So I label it hypotenuse. Okay? I'm going to find the opposite side to the angle that I'm interested in. So down here, BC would be the opposite side. Okay? And then I find the adjacent side. I always find the adjacent side last. It's usually the one that people struggle with the most. So if I wait till last, there should only be one segment left for it, so they go together. Okay? I get a lot of people who think the hypotenuse is adjacent, and I would argue that it is. But being a hypotenuse supersedes being adjacent. So we're going to call it hypotenuse instead. Does that make sense? Okay. Now, the words sine, cosine, tangent, they have, like you've probably never heard those words or used those words. Where do they come from? Don't worry about where they come from. They have a history. Okay. And their sine, for instance, if you were to look it up, like its initial use, the word that was meant to explain what we're doing here in another language was similar to SINE, okay? and it got translated into multiple languages, and through like an error that was made in translation, it got changed over to sinus, which is talking about the sinuses in your face, okay? And then another translation that went to SINE, which is what we use here. Back in its original language, I don't know what language it was, it referred to the idea, and it's working with, maybe eventually I'll show you the picture with circles and all that kind of stuff. It's trying to compare this segment here to that segment there, okay? And that's what we're doing here, okay? So sine, don't worry about why is it called sine. That's not a big deal, okay? Sine of angle A, and usually we'll put parentheses around that A, okay? What it means is that it is the ratio, which is a fraction, right? Or the comparison of two numbers through division. And those two numbers are always going to be the opposite side divided by the hypotenuse. Is that okay with everybody? So whenever somebody says sine to you, okay, or find the sine of this angle, or the sine of that angle, or whatever, you're going to, what they're asking you to do is find the opposite length of that angle, okay, so find the side that's opposite the angle, take that length, and divide it by the hypotenuse length. And that fraction, or that ratio that you get back, is the sine of that angle. Okay? Is that okay with everybody? Cosine, okay, and when you take trig, we'll talk about the relations between sine and cosine a little bit more detailed, okay, and greater depth. But the cosine is the relationship between the adjacent side divided by the hypotenuse. The adjacent side divided by the hypotenuse of a predefined angle of interest. Okay? And tangent is the opposite leg, or the opposite side, divided by the adjacent side. Okay? So there's three ratios that we need to commit to memory. And people get them confused. Okay? So a long time ago, somebody developed this mnemonic device, this phrase, called Sohcahtoa. Have you ever heard that before? Okay? So Sohcahtoa, the S, the C, and the T stand for sine, cosine, and tangent, respectively. Okay? So the first letters in that, each one of those three words refers to the trig ratio, the trig word we're interested in. And then the next two letters are numerator, denominator. So O stands for opposite side, H stands for hypotenuse. So S-O-H, we read it that way. Okay? C-A-H and then T-O-A. And that, if you remember that phrase, it should help you remember what sides get compared inside of which trig ratio. That make sense? Kind of like King Henry died by drinking chocolate milk, right? We've heard that before. So Sohcahtoa is just another one of those types of things. Okay. Now, what we need to realize is, like when I say the sine of A here, the sine of A, if I look at the opposite side, so it's opposite of hypotenuse, so the opposite side here would be BC. Does that make sense? The hypotenuse would be AC. Okay? The cosine of A would be AB over AC. It's the adjacent side to that angle divided by the hypotenuse. And the tangent of A is equal to opposite, which is BC, over adjacent, which is AB. Okay? Now my question to you is, what happens when I ask you to reference a different angle? So let's say I'm more interested now in angle B. So I ask you, what is the sine of angle B? Okay. Well, I'm sorry. I didn't look at the way I labeled this. I'll never ask it about B. We'll never ask this about the right angle. I should have said C. So I'm interested in sine of angle C, which is basically we're only going to ever do these three ratios for the acute angles in a right triangle. Okay. So if I look at C, does that change the labeling of these two sides here? Is this now opposite, and is this now adjacent? Does that make sense? Because now I'm focused now on this angle of interest. So now the sine of C would be AB over AC. The cosine of B, not B, C again, sorry. Cosine of C would be BC over AC. And then the tangent of C would be AB over BC. So sine, what I'm trying to get at here is the ratios depend on what angle we're focused on. Does that make sense? Because we see that BC over AC for sine of A is different than AB over AC, which is the sine of C. Okay? But what do you notice? That there and that there, those are the same, aren't they? Is that okay with everybody? You see AB over AC being the same? So that tells me the cosine of A is the same thing as the sine of C. Well, think about it. Get your calculators out real quick. If I go to, and I'm going to do this on Desmos in front of you. I'm just going to use the scientific calculator for that Desmos offers. Okay, it would be really no different when you use the graphing version. Okay, but in every calculator there is a key that you have to make sure is turned on correctly. Okay, and it's usually, we call it the mode. Basically what it's doing is flip-flopping back and forth between two measurements of angles, two units of angle measurements that we use all the time. Okay, what unit are you guys most familiar with in regards to angle measurements? We use degrees, right? Okay, it's much like if I ask you what unit are you more comfortable with if I asked you the distance between Lima and Cleveland. What would be the unit you're most comfortable with? Miles. But could I measure that in kilometers? Yes, you could. Okay. Now, if I told you that answer in kilometers, would you have a real good sense of how big it is? Probably not, right? Okay. Angles are the same way. There's a second unit that we deal with in regards to angles that you've probably never heard about. They're called radians. Okay. So if you look on your calculator, okay, there should be. So I'll break them all down here briefly. If I look at Desmos in this version, it's easiest here to see. You see where it says degree right here? There's a toggle switch. If I hit that, now it says RAD. So now it's in radians. Now it's in degrees. Okay. We are going to be working primarily in degrees. Okay. Primarily in degrees. So I want you guys to take your calculators, and I want us to right now to figure out, how do I go from radians to degrees? How do I make sure I'm in the right mode? So on Desmos, on that version of Desmos, that's how you do it. On this version of Desmos, you got to hit the wrench over here. And you see down here where it says radians and degrees, that's the toggle. So I'm going to highlight the one that I want it to be in. Okay. If we're on a TI calculator, okay, so TI 83, 84, 89. If I go to, you see where it says mode? Okay. You're going to click that, and it's the third or fourth line down here. You see where basically it's the same way as Desmos. I need to toggle that on or off. Okay? If you have one of these calculators that is like my red ones, okay? You see the yellow second key at top left, right? You see right next to it where it says DRG. D stands for degrees, R stands for radians, G stands for gradients. Okay? You need to hit that button. Okay, so when I have this calculator on, in the bottom right-hand corner of my view screen, it should say either DEG, RAD, or GRD. Okay? I'm going to push this button that says DRG as many times as I need to where that little word down there on the bottom right-hand side of my view screen says DEG. Does that make sense? Okay. What stinks about this, think about this. If you did a problem about distance, let's say distance equals rate times time problem, and you are provided everything in regards to that problem in kilometers, okay, but you use like a rate that was figured out using miles, okay, you could still go through the algebra and get, do everything correctly. But because you have wrong units, your result is going to be wrong. Does that make sense? Okay. I could teach you everything. You could put everything in the right spots and do all the algebra by hand. And when we turn to our calculator to calculate something, because our calculator might be in the wrong mode, it's going to give you the wrong answer. Does that make sense? So you always need, when we're using sine, cosine, and tangent, every single time you pick up a calculator, you need to make sure that the mode is in DEG. It's in degrees. Okay? It's not a huge deal this year because I don't let people use my calculators because of COVID, but in the past, I teach trig. In trig, we want our calculator to be in radians most of the time. So my trig students, first and second period, would take my calculators, change it to the right mode, do all their work for that class, throw the calculators back in the box. Geometry students come in, grab the calculators, they start plugging away, and all their answers are in radians, and everything is wrong because they didn't check the mode. Does that make sense? If you lend your calculator to somebody, make sure that when you get it back and you start doing this stuff, you make sure it's in degrees. The number one error, and they've fixed this, I think, that happened a few years ago on the end of course exam. So the end of course exam, this is why I've been trying to get you guys to use this. This is the calculator that you get on the end of course exam. Okay? They remove some of the functionality of it, but that is the nuts and bolts of the calculator you get. When they first started using Desmos on the end of course exam, it was defaulted to that. But every problem that dealt with sine, cosine, and tangent was given a degree. So you had to change the mode. Does that make sense? About 95% of my students didn't do that. They did all the right work, got the wrong answer because they're relying on a calculator that they didn't know how to operate. And they forgot to change things in the mode, the right mode. In addition, so this is what stinks about the end of course exam, which you guys are still taking right now. Okay? When that question pops up, it's much like the interface of it is much like Math XL. If you guys remember taking the end of course exam for algebra, right? Gives you a question. You have a calculator option in that question. Open the calculator up. You can open it up. Okay? In that problem, you change it to degrees. It started at radians, you change it to degrees. Okay? Answer that question. Go to the next one. It's a new page. It's a new link to open a calculator. It's going to open that calculator, and it's refreshed back to what it was at the beginning. Does that make sense? It doesn't save what you've already used the calculator with. Is that okay with everybody? So every problem on that thing, you may have to flip back and forth between degrees and radians. We always right now want to be in degrees, so that's just something you have to pay attention to. That kind of makes sense? Okay. What I was getting at there, though, think about this. If I type in sine of, now I'm going to type in an angle right here. Okay, now this is where things get confusing. This is not the number I want because I'm in the wrong mode. I want this to be a degree. So there's a degree. I get 0.5. Okay, so those of you that have your handhelds, if there's two lines on your view screen, this is why I like this calculator or I like Desmos. So there's two lines. I can see what I typed and I can see the answer that goes with it, right? In two lines. If you have a calculator like that, you can just type it in like I have up on the screen. Okay? Can I see your calculator? If you have one of these calculators where you only have one line on your view screen, you have to type in things backwards. So you actually have to get that 0.5, you have to type in 30 first, and then hit your sine key, and it'll give you your 0.5. Okay? That calculates not bad right now, but eventually when we start getting more complex problems, there's so much that you got to reverse and do backwards that calculator will give you headaches. Okay, Desmos is a calculator that you can type things in as you would have written it by hand, and it just makes things so much easier. The order of operations are more convenient. But there I get sine of 30. Okay, it is 0.5. Looking back at what we were saying here, okay, so if A was 30 degrees, what would C have been? This is a right triangle. If that was 30, C would have been how many degrees? 60, right? Does that make sense? Okay. Right here, what I'm saying, okay, this relationship, or it could be this one right here, okay? We're saying that the sine of 30, if there was a 30 degrees right there for that A, it's going to give you a ratio of 1 to 2 back. This is saying that cosine of C, so C would be 60, right? Should give back the same 1/2. So let me show cosine of 60. See how it gives me the same 1/2 back? Okay. What I want us to realize is that the sine of 30 does not equal the cosine of 30. The sine of 60 does not equal the cosine of 60. However, the sine of an angle always equals the cosine of the complement angle. Okay? So in practice, it looks like this. If I take sine of, I'm going to call my angle, this is the Greek letter theta. Okay? Usually in trigonometry, we use Greek letters to represent angles. They're still variables. I could use X or A or B or whatever I want to here, but we usually use capital. I mean, they don't always have to be a capital, but we use Greek letters. Okay. Basically, what we come up with is that the sine of theta is always equal to cosine of 90 minus theta. Okay. If we were to graph this stuff, you guys know about like light waves, sound waves, electromagnetic waves, which are like Wi-Fi waves, Bluetooth waves, microwaves that cook your food, that kind of stuff. They are, now sound waves are a little bit different. Sound waves they're compression waves. So, but they can be modeled using, so if I use the sine of X, so sine, and this is what we get into a trigonometry class, is understanding where did this curve come from. But that right there is how Bluetooth, how radio waves, how microwaves, how light, how those things travel. Okay. Here is the cosine wave, the red one. Okay. Now I'm in. It's kind of confusing. I don't know if I can change this or not for us. Let's see here. Angle unit, radians, degrees, minutes, seconds. To show that these two things are the same, actually, let me do it here. Because I got to do some calculations. The way that GeoGebra is built, it's not really all that easy for students to see. But let's do it here. If I take the sine of x, so sine of x here, and I graph that. Now it's going to look kind of messed up right now because the sine needs to go between 0 and 360, and right now I'm only showing it going from 0 to like 10. So I'm going to change my window here real quick, and I'm going to go from negative 360 to positive 360. I want my x scale to go by, we'll just go by 50s. This needs to be between negative 2 and positive 2 is fine. And now you can see the kind of the up and down of that. Okay, so each one of these, that's 50, 100, 150, 200 on the x-axis. Okay, everybody? So that's the sine function. The cosine would look like this. Be this red one. Okay. What we wrote a minute ago right here was that the sine is the same thing as 90, the cosine of 90 minus theta. So if this is x, it'd be 90 minus x. So what I'm going to try to do is I'm going to rewrite this here, this cosine, this red graph, as instead of cosine of x, I'm going to go 90 minus x in graph. So we get the blue one, which that's the sine. And now we're going to graph the red one, which is the cosine of 90 minus x. Do you see that no matter what x we use, the red one and the blue one are identical? Okay, so that is outside the scope of this course in regards to the graph. The graph is more a trigonometry, and I really haven't even gotten that far with my trig students yet this year. But if you have interest in trig, that's what we get into. But in order to understand that eventually, we need to understand these relationships that we were seeing right here. That if I put x there, then to make these two things equal, that's got to be 90 minus x. Okay, now it doesn't know what x is, but let's go, oh, I don't want to do that. So cosine 90 minus x. Now if I say x is 10 degrees, it's putting x in here, it's putting x in here, so the sine of 10 and the sine of 80, or so sine of 10 and cosine 80, they're the same thing. Okay? 20 and they're the same thing. Okay? Now let's talk, we haven't gotten this far yet, but let's talk about what these two numbers really mean here. What does 0.342 mean to us? Okay? So, going back to this here, okay, is talking about, and I don't want you to write this down. I'm going to use GeoGebra to explain this a little bit better than what this written statement says. But it says similar right triangles have equivalent ratios for their corresponding sides. Okay, let's look at it. And this is what we talked about in, I think it was 7.2, 7.3. If I have a right triangle that is, let's say, that right triangle right there. Let's call this angle A. Just for convenience sake, because of what we know already about special right triangles, let's say that this is 30 degrees. Okay. let's say that this is, well, I don't want to put labels or sizes on this yet. Let's just say we've got that right there. Okay, we've got that red triangle. Okay, let's say that we put on top of that this blue triangle. Okay, so the red triangle, let's just call it A, B, C, and we'll call the blue one, we'll call this B prime, I'll call that point C prime. Do you guys agree that point B kind of compares to B prime and C to C prime? Do you guys remember what relationship we have now between that red triangle and that blue triangle? Let's say I did something like this. Let's just completely separate them. So again, this is still angle A. Still angle A, still 30 degrees, right? Anybody remember a relationship between these two now? That because they have that angle congruent to that angle, and this right angle congruent to that right angle? What is true about those two triangles? They're similar, okay? They're similar. So triangle ABC, okay, which is this red one, is similar to triangle A, B prime, C prime. Is that okay? That means then that AB compares to A, B prime, just like BC compares to B prime, C prime, just like A, C compares to A, C prime. Is that okay? I'm going to compare, I don't want to look at all three of these ratios, but we can extend what I'm about to talk about with all three ratios. I want to look at, let's see here, B, C, and let's just look at these two. Okay. We know that to be true because these were similar triangles, right? Okay. Now this information, okay, if I look at that, that is coming off of taking BC over B prime, C prime. That's comparing this distance here to that distance there. It's going from red triangle to blue triangle, correct? I'm going to make a quick alteration. Can I, because of what we know about proportions, can I change that statement there with that one? And I still have a true proportion, right? So I'm going to do that. When I do that, that's going to generate BC over AC equals B prime C prime over A C prime. Now, the reason I want to do that, okay, now look at what I'm comparing. If I compare, look at this first fraction. Now I'm comparing BC, which is that side right there, to AC. I stayed in the same triangle, didn't I? Previously, it was jumping from one to the other, comparing one part here to one part here. But now comparing this part to that part. And if I look at this one, this right ratio, is it comparing B prime, so this was B prime C prime, to A C prime, which is that? Is that the same comparison of parts that we compared down here? Does that make sense? Would you agree that that's the opposite side to 30? And that this is the hypotenuse? So right there, that would be opposite, and that would be hypotenuse. Is this right here the opposite side to 30? And is this the hypotenuse to 30? or that hypotenuse of that triangle, which is that right there. Does that make sense? So what we're arguing here is if I have two triangles that are similar, they have a right angle and then an acute angle that is also congruent, then the way that I compare their opposite side and their hypotenuse should always be the same. So if I gave every one of you a different right triangle, okay, but every one of you had a right triangle that was that had a 30-degree angle in it. Does that make sense? So some of you got one that's really tiny, some of you got one that's medium-sized, maybe some of you got a bigger one, maybe somebody's got one as big as the room, somebody's got one as big as the courtyard, okay? But every one of those right triangles has a 30-degree angle in it. When each of you measures the opposite side, whatever your distance will be, and you divide it by the hypotenuse, whatever that distance might be, okay, every single one of you is going to get 1/2 back. And the reason I know we're going to get 1/2, and this is why I use 30 degrees, didn't we know that in any 30, 60, 90 triangle, that across from 30 is n, right? Across from the right angle is 2n. So if I gave every one of you a 30, 60, 90 triangle, okay, and I asked you to measure the side across from 30 and measure your hypotenuse. Let's say every one of you was different size triangles. When you found your two values, one is going to be double the other. That makes sense? Because of what we know about 30, 60, 90 triangles. Also because of what we know now of what I just demonstrated here. Okay? But no matter what, okay, so if somebody has n to be 1, then this would be 2, right? If somebody had n to be 4, this would be 8. Okay, if somebody had n to be 41, okay, this would be 82. But when I compare opposite side divided by the hypotenuse, what's n over 2n always reduced to? 1/2, right? Okay, so now I need a tool that links me to that 1/2, and it links me to dividing the opposite by the hypotenuse. So that tool, that notation that we use, we say it's the sine. We focus on the angle of interest that identified this to be the opposite and that to be the hypotenuse. And we get sine of 30 equals 1/2. So this right here is telling you that no matter what triangle you look at, if it's a right triangle, and you label things in regards to your 30-degree angle as opposite, adjacent, and hypotenuse, that when you look at the opposite side of a 30-degree angle and divide it by the hypotenuse, no matter how big those values are, they will always reduce to 1/2. Does that make sense? Okay. So let me show you this kind of actively in GeoGebra. Okay, right here I've got, and these are, again, using values that maybe we're comfortable with, that we're familiar with. 45 degrees, again, is from special right triangles, an easy angle to understand. This should be the side BC should be in, and this should be in, right? Okay, and this is in radical 2, correct? Okay, so I want to focus on this angle down here that has the blue hashing in it. Okay, and I can create any triangle that I want of any size. Okay, and right now what I want to do is I want to show BC and I want to show AC. Okay, and I can change as I move this, it changes those sides, right? But when I divide those two things, what's going to happen when I compare that side and that side through division? You get 1, right? Okay, so let me show you that algebra here. Okay, as I move these, different triangles, different values here, right? But their quotient always ends up being 1. Does that make sense? So, what trig ratio uses opposite divided by adjacent? Tangent. So if I ask my calculator, what is tangent of 45, you see how it spits back 1? It's telling me, regardless of how big these two numbers were, you know their quotient is 1. That's what the output that the calculator is providing. Okay, so let's do a different one. Okay, let's go let's go with those two. Okay, so right now we've got adjacent and the hypotenuse highlighted, right? The adjacent and the hypotenuse. Which trig ratio uses adjacent and hypotenuse? Cosine. So I'm going to come to Desmos real quick. I'll just get that star, type in cosine of 45. It gives me 0.707. Okay. Well, if I take those two values, which is AC and BA, so it'll be this first one. Okay. And as I change the size, we can do the rounding to get that 707 that Desmos was giving. It is dividing that value by that value, and we're getting that quotient, right? But that triangle, I don't know if I can trace the whole thing. That triangle is no different than any of those other triangles there, right? Other than, terrible when it traces that way. But you kind of see that on my screen, you can see the gradient change a little bit, so I can see multiple triangles here. But these triangles are all similar because they all have a right angle and have a 45-degree angle, right? So it doesn't matter the size of the sides; they're always going to relate to one another in a radical 2 comparison. Does that make sense? Which when I divide that, n divided by n radical 2, it always gives me 0.707. Does that make sense, everybody? Now, the triangles that we've been dealing with the most so far are the 45, 45, 90, 30, 60, 90. Okay? Basically what Sohcahtoa is, because our 30, 60, 90, 45, 45, 90 templates only work for those triangles, right? Two types of triangles. Well, what if I have a triangle that has a 29-degree angle in it? A right triangle with a 29-degree angle in it. I can't use a 30, 60, 90 anymore because that's not 30, 60, 90, right? 29, 61, 90. Okay, that's a problem. Sohcahtoa takes care of that for us. Sohcahtoa is essentially the template for all other right triangles, okay, that are not 30, 60, 90, 45, 45, 90. Although Sohcahtoa does work for 30, 60, 90, 45, 45, 90 as well. Okay. Comparing it to something like algebra, so we've got tools for factoring, like, well, shortcuts for factoring, right? But what is the thing that always works for factoring? You remember the formula for always being able to factor something? Do you remember the quadratic formula? So that's like kind of the safety net or the catch-all. If I don't know how to factor something, run it through the quadratic formula, and it always gives me the result. It always gives me what I'm looking for. Okay. If I don't know how to use special right triangles, my safety net is Sohcahtoa. Okay. Sohcahtoa might not present things in the correct format if I'm working on 30, 60, 90, 45, 45, 90. Usually with special right triangles, we want things left with radicals. Sohcahtoa will never produce a radical for me on my calculator unless you have like a $300 TI-89. Okay. So we got to keep that in mind as we move forward, but it shouldn't be a big deal. So what happens then is like, okay, so what if I do have a 28-degree angle? Okay. So my sine, well, let's make it even greater. Let's make it 29. Okay. That's pretty close to a 30, 60, 90, right? So the sine of this thing should be, if I say sine of 29, it should be pretty close to 0.5 because the sine of 30 is 0.5. Does that make sense? Because in a 30, 60, 90, the opposite divided by the hypotenuse is n over 2n. So let's look at these two values. Let's look at BC and AB. BC and AB. Okay. If I look at those, that pretty close to 0.5? Does that make sense? So it's showing me, and I can go out to however many decimal places I want, 15 decimal places, okay, that my two sides, my opposite side of my hypotenuse of any right triangle that has a 29-degree angle in it. The opposite side divided by hypotenuse is always going to be in a ratio of 0.4848096202463337 over 1. Does that make sense? Okay. So we can use that then as, you know, if I've been giving you guys let's see here. In a 30, 60, 90, when I gave you the hypotenuse, to get this side, you divided by 2, correct? Or multiply. When I divide by 2, that's the same thing as multiplying by what? Multiplying by a half, right? Okay. So if I gave you, say I had a 30, 60, 90, I told you we are going to take a side hypotenuse of 14, and I want you to tell me the side that's opposite 30. You would take 14 divided by 2, or 14 times 1/2, right? Okay. Or 14 times 0.5, right? Well, now if I tell you you have a 29-degree angle right here, and I ask you, what is this side? What you do is you take that number right there, you take your hypotenuse, and instead of multiplying it by 0.5, you now multiply it by that number right there. Does that make sense? So it's essentially that's a scale factor. Okay. Now you're never going to know that number. Okay. You're not going to commit that to memory. That's a fact. Okay. It's much like knowing that there's 5,280 feet in a mile, right? Okay. So when I look at the sine of 29, it is always that number, that 0.484 number. But when I ask it to be 28, when I ask it to be 28, it's a different number. Ask it to be 26, different number, right? So you can see that it would be very hard for us to memorize all those scale factors, correct? So our calculator is programmed to know what those are. Does that make sense to everybody? So when I type on my calculator sine of 12 degrees, okay, is see sine of 12 degrees. Now, and this is something we get into my trig class, that my calculator is actually using an approximation, but it's far enough off that that's not a big deal to generate this value. But when I go second quit calculator, let's see here. When I hit sine of 12 degrees, it knows that that is essentially a symbol for this scale factor. Is that okay with everybody? Going back again, if that was sine of 30, your calculator knows that to go from the hypotenuse to the smaller side, the scale factor is 0.5. Okay, so that's what those numbers are. Hopefully that makes sense. When I was in school, and I always go back to, a lot of times I teach the way I do because of how I experienced high school math. That was never explained, okay? Which it was explained, and 15 of you, if 2 of you got it, I'm happy with that at this point, okay? The hope is down the road as we see this for 3, 4, 5 different days that it starts to sink in. It starts to make sense. You make connections. If you can understand that, it makes everything else later a lot easier. Does that make sense? From my perspective, when I was in school, it was monkey see, monkey do. Be a robot. Okay, I'm going to show you how to do it. This is how you do it every single time. Not show you why, not show you where these numbers from my calculator are coming from, and it made other things hard. Okay, so that's why I spent a lot of time explaining that. But these values that are programmed in our calculator, okay, are the scale factors to enlarge or reduce a hypotenuse to come up with a side opposite, side adjacent, or whatever it may be needed. Okay. On Wednesday and Thursday of this week, I'm going to pick up with this. My hope is on Friday to have a short quiz for you over special right triangles and kind of an intro to what we're seeing here with the sine, cosine, and tangent. We're going to spend quite a bit of time on sine, cosine, and tangent for several reasons. It's a big portion of your end of course exam. If you've taken the ACT or plan on taking the ACT, the last handful of questions always deal with sine, cosine, tangent. It is, the other day I said of the 5 things, special right triangle is one of the top 5 things in mathematics that you need to know in high school because of how much it's used. This is right up there in that top 5 as well. Okay, so we'll spend quite a bit of time on this. My hope is that it becomes something that you have a concrete understanding of. It's not abstract to you, okay? Because it's something that can be very easily construed to being abstract. So I want to make sure that doesn't happen. No homework tonight.